All the theoretical part, we do not, I don't think we go back to any equation or theory anymore, so it's more hands-on now.
Yes.
So we start the partner design.
Yes.
I try to ask one of my students to teach the PCB software. You don't have to use that, but because there may be some more user-friendly free version, etc. But we use a very professional one. So I recommend that. We don't have Altium. We use Ecgr, which is not user-friendly, but that's the standard. One of the better ones. And perhaps you're kind of familiar with some of the interfaces because it uses the same platform as PSpice, if you have done that before. So perhaps I could do it, but I use version 10, now it's version 17. So I thought maybe it's easier. But we have also the video recording, so you can go back. Most of it, I think, because it's very hands-on, I would like you to practice. So the second lab that we define is basically turn in the manufacturing files without ordering.
Oh.
Right? So obviously you can go ahead and order. These days it's so cheap.
Yes.
Even with 25% tariff on China, it doesn't go more than $10. So it's super cheap. I can tell you in my time, which is not so long ago, I used to spend $1,000 on every order, or $2,000, right? So my students, they order less than $10, right? With shipping, DHL is $12. So I have a theory, but I mean, it's not that important, but I think everything is logged in Chinese factories. That's my guess, and they try to figure this out, how they can use it when they know the source.
Of course.
So that's why it's so cheap. Otherwise, even if you want to use that copper and buy that copper and all the tooling, it should be more than that.
That's no theory.
Right? Because when I was in industry, I remember we had full-time engineers. These days, you cannot find cheap engineers anywhere. But they were just downloading US patent and relate them with companies. And they let other departments to take care of what people are doing. So, and that was the practice. That was a practice in all the American other companies. Basically, they hired cheap engineers in China. This is how they, in my view, trace other companies, because nobody talks about what they do, right? But through patents, they got some ideas. So now, that was just pure metadata that they would get from those things. Imagine they put you on the medical device sector, you just download files based on your knowledge, you classify it. So that's someone else's problem to dig into that. So now these files with emails, files, everything, so easily transferred. So that's my guess. But the good thing is, for you as a student, it lets you try 100 times more than what I could do, right? Because you'll see, I cannot emphasize more. So for the next 2 months, you become an artist. You're no longer an engineer. You have an empty canvas, and you try to paint it. You like it or you don't like it. I'm not a good painter, I'm the best designer. So I draw paintings. right? And you will be one of them, okay? And nothing is perfect, and you know, as I told you, we need patience, but also we need speed, which is very contradictory. So what I'm trying to get to for your next assignments, we just want the manufacturing file verified by one of these basically companies, whether in China, in the US, we use the US company for verification, 4pcb.com, right? For some of you, if you're on scholarships that they need to be American made, it's another great resource. They have student, promotions. So if you do 2 boards, basically it's $33 a board, and if it's 4 layer, it's $66 a board plus shipping. So still not very bad. But the mechanism to test it is good. So your deliverable is basically design and prepare the manufacturing files for a hardware that can be interfaced between your inverter and the microcontroller. So I think from this week you can get 1 microcontroller set from the TA. So that is given. So we will provide the DC to AC converter that I think you have tested. You went to the lab once. I think you will go to the lab 2 weeks to test another basically module. And what you're doing is designing this board. Right? Signal conditioning circuits. And depending on the complexity of the control system that you design or developed within your team, portion of it submitted as your lab 2-2, right, would be incorporated. We just show the simplest version of it. But we'll see. So today, I think, again, today I'm going through the basic of sensors, what should you buy, and next week you go to the PCB tutorial class. But again, I recommend you guys start if you have time. From next week, I think we have 1 soldering sessions, so that you have an idea when you're designing the boards, what needs to be considered. I think you already used some sort of breadboard in the past.
Yes.
Right?
It was like blue one, what was that?
Yes.
Yeah, so I think that through-hole devices has no place in the electronics industry. Nobody used that.
Okay.
But the SMD, where surface mount, is the only one. So you really want to understand the value of clearance, pads for soldering, right?
Yes.
So how much support you need to provide. And again, these things can take months and months to choose, right? And unfortunately, you don't have the DG key list and filter, right, to trim your preference. Okay, so really it's a design choice, but as I said, honestly, it's so cheap these days that I don't know if I should emphasize on this anymore. If I were you, I order a board per day, right? And you will be master of it, and whatever ChatGPT extension does, you can review with a smarter eye. So So with that, what I'm requiring in a digitally controlled power converters or any other things, robots, etc. So the interface, so the general feedback control, right? We saw the benefits, and for that, whether you observe it or you sense it, we bring it to the microcontroller. So this interface, should be prepared, and that's what we overall I want to talk about because the components are not selected. So, what do we need, right? So in general, the photovoltaic system, as I said, is voltage controlled current source. So one way to track the sun is to control that DC link voltage. So the first thing that you need measurement for is the DC link voltage. Then we talked about the single versus double loop systems, and we saw that at least in our systems where you have at least one inductor and one capacitor that exhibits a second order system. So if you use a simple PI compensator, PI is a first order system. So with a first order compensator, if you do with the second order system, it may not be optimal in terms of power quality. I don't know if you have tested it or not, but we show that by splitting into two first order systems, meaning having the current loop and the voltage loop, we get faster and better quality waveform in the output. So in other words, you not only need the DC link voltage measurement, but also AC side current measurement. Okay, so these are like absolute must in your system unless you're bringing more intelligence to the system. So we are not talking about that now.
Oh.
So the conditioning circuit in the simplest form, it requires DC link voltage or DC voltage measurement system or DC voltage sensor, right? And AC side current sensor. It should be interfaced to a microcontroller. Okay. So these informations basically are the voltage and currents, typically in analog form, right? So it's continuous. Whereas the microcontroller is a digital interface, right? So therefore, either the microcontroller can provide the A to D conversion, or you do it, or the sensor has a built-in, right? So this is what I'm saying. It's very difficult that all of you come up with the same design, right? But again, I still encourage discussion and even copy what I'm doing. Okay, so the first thing is, well, defining the parameter. Once the power stage and the power electronics engineer basically come up with the basic system, invites the firmware guy to come on board to design this conditioning circuit. So what signals we need, and now based on either the company experience or what we have in this case, our microcontroller kit has ADC built in, so you can read through it. So for instance, this particular one has 12-bit ADC. The input is 0 to 3 volts, right? And these are the things that we talk later when we talk about the ADC sampling, etc. But as you can see, if you want to use the analog interface of the microcontroller, right, you cannot just apply any voltage, right? It has to be limited between 0 and 3. That's the first thing. So if you go above that, right, or out of this range, you may damage the microcontroller or your controller doesn't see it. Right? Does that make sense? So again, on the digitization, I think we'll talk about it later, how things needs to go back. All right, so you go to your systems that you're trying to design. So for instance, in this case, you chose this inverter. In your case, you refer to your simulation setup. Any questions?
They were asked about the presentation.
Is it on Canvas?
Or the PowerPoint.
Should be.
We'll find it later.
Well, I think because the inventory changes all the time, you know, I think, you know, the slides and the choices are diverse. But I think the concept is more important here. So you have to go back, okay, what do you want to control and what are the parameters here? So in this case, you have only single panel, right? So essentially, your maximum voltage, you have to consider that. In this case, for instance, it can be a 50 volt or 60 volts system, right? During open circuit voltage. So your voltage sensor, right, should measure 60 volts, right? So if you want to do 60 volts, but your microcontroller only accepts 0 to 3, what should I do?
Current sensing resistor.
Right? So you need an interface that converts this range to 0 and 3 range, right? Prove me wrong, but I cannot find many good voltage sensors in the market,
Oh.
right? So basically what I do usually in voltage sensing, I design my sensor from basically voltage divider, right, and buffer circuitry that we know from electronics. Okay? So in other words, for voltage, I don't think you have any choice but just building your own circuitry, right? So basically you're converting 0 to 60 to 0 to 3 volts. So you should provide this mapping later on to the firmware engineer, right? So that he knows that how to read this, because what you see in the microcontroller is a value between 0 and 3. So that's why the software engineer dealing directly with the hardware people, right? What am I reading here? When you go to other parameters such as speed, right, position, electric current, right? So basically for that, it's usually we use a detector, right? And it can be in form of magnetometer, so magnetic field detector. So the magnetic detector essentially reacts, the detector reacts to the magnetic field change in the system, right? So imagine the position, imagine you have a magnet that rotates. So if you place another magnet or detector whose value may change because of that position, if you create a bias, it gives you an output proportional to the position with the reference. For current is exactly the same, so you can use a magnetometer to do that. So what are the different technologies in current sensing, right? So you have the first technology that everyone knows is not magnetic base. It's basically measure the voltage across a resistor, right? From a designer's perspective, right? So that's very good. But you don't want this resistor to have big tolerance, right? Because you now, let's say if you want to say it's 1 ohm, right, but it's 1.5 ohms, then that doesn't do your job, right? If your application, let's say in case of solar, it's outside, if it's varied by temperature, right, significantly, then again, it doesn't. So therefore, when you want to design a good current sensor based on simple resistor, you're looking for specific resistor known as shunt. They call it shunt resistor or current sense resistor. But because you're measuring the voltage, again, all the things that you would do for a voltage sensing applies. So in other words, you need extra work, right, to build your own sensor. The other sensors are based on magnetic field. So when you have the current passing through a cable, trace, conductor, it generates a magnetic field, right? The simplest one is the current transformer, right? So the magnetic field that is induced, if it's changing, basically it gives you the output. So there are several examples of that, right? So one, let's say, is this one. Right? So for instance, by lamp. So as you can see, it has basically a magnetic detector circuitry, right? And the output is determined by an external component defined by the manufacturer, right? So you have to go through the data sheet to really see, like, okay, how should you operate this particular sensor? So for instance, if your bias is 12 volts, right? It says if you want to measure plus minus 50 amps, the R, right? If the ambient temperature max is 70, should be between 10 and 100 amps. So in other words, depending on the technology that you're picking, right? You have to essentially design this. So what we need, right, is go through like, okay, what's the turn ratio? What is my output? So for instance, if the primary is, let's say, 20 or 50 amps, right, the secondary, depending on what type of sensor you're picking, is now this value, right? And now times the R, basically what you get is this value. So in other words, the choice of sensor and sensing technology that you guys are responsible to acquire, right, determines what value and what conditioning circuits you're using. So the first, you have a question? No? Okay. So for instance, when you're dealing with, let's say, 50 amp application, right? For instance, you cannot just go with, okay, let me choose a 50 amp sensor, right? So you want to create some, cushion on the top so you have some margin. How much is that? 20%. Nobody knows, right? Typically determined by the price and the past experience of the company and designer, right? So in this case, you are looking for 55, I just picked 57, right? So then it goes, do I have unipolar current measurements or bipolar?
Oh.
So if I'm measuring the grid current, it's AC, right? So essentially, this particular sensor gives the bipolar output. So if it's 57 amps, and if I pick 100 ohm, it gives me 5.7 volts in the output when it's positive, and negative 5.7 volts when it's negative 5.7 when it's positive. So can I insert that into my microcontroller? No. So basically what will happen is clamp at 3 and limit at 0. So you lose information if not damaging the microcontroller. Right?
I see.
So that's why I'm saying the divergence starts to happen now, right? Copying becomes more challenging because the choices are different. So if you pick, for whatever reason, this technology, which is one of the most accurate technology in current measurement, right? So you have to come up with a circuit to not only provide the conversion, but the transformation from a bipolar system to a unipolar between 0 and 3 volts. Yeah.
Could we use RMS in some way to do that?
I don't think firmware for power electronics control. Well, I mean, you can, but what do you mean by RMS, right? So if you're saying RMS at 60 hertz, no.
Okay.
You're controlling at the switching speed, right? So if you do 60 hertz, meaning that you want to reduce so your controller cannot be faster than 16 milliseconds,
Okay.
right?
Yeah.
Because that's the RMS. But if you mean by RMS, is RMS of the switch current, switch cycle, yeah, you can,
Yeah, that's what I
you know?
meant.
In fact, the firmware engineer, basically, that's not the only thing they have to do, right? Essentially, they have to run the converter. Believe me, I mean, it has a lot of issues with these noise control and request from, let's say, Duke Energy says, okay, I want this command to be implemented, right? So the firmware engineer does not give you any margin to say, okay, now calculate the RMS for me, because everything is sampling, right? So I'll talk about it later, but essentially, you know, so your inductor current looks like this, right? So the average, okay? So, again, this is something that our computer engineers, not necessarily because they are computer engineers, I mean, like whoever's doing more firmware engineering in your team, right, can decide about this, right? So this is the PWM cycle, right? So where do you guys want to measure this? So obviously you cannot measure like all of this like this,
No.
right? Because the microcontroller has certain clock, right? So in other words, you are doing this digitalization anyways, right? So then how do you want to implement the code, right? So some of you, I think, have done some microcontroller programming,
So probably
right?
sync.
So essentially you have certain time, right? Synchronous or asynchronous to do certain tasks, multiplication, right? Some for loops, whatever, right? So in other words, if you want to do this, synchronized with your switching, then essentially you have this much time to do everything else, right? Send this flag, control this, okay, right? So nobody, no firmware engineer allows you to basically use his budget easily.
But we
Right?
could do like every 5th, right?
So that's what I'm saying. So
Okay,
if
yeah,
you do
perfect.
this, so you're reducing the control bandwidth,
Yes.
right? So basically, you're investing in things and now you're not using it, right? So therefore, what they do is, imagine if it's high frequency enough, they assume that this is curve, like constant, right? So if they're well synchronized with this, they shift 90 degrees or 100 degrees, and they sample only these points, right?
Just simple.
And if this is they can synchronize the ADC sampling at this point, they are capturing RMS automatically. They don't implement RMS calculator
Yes.
the way that we think,
I see. Yeah.
right? So we do it, but this way. And not only because of this, because you always get a lot of noises here. And if you do in the middle, there's a chance
Okay.
that you are away from noises,
Interesting.
right?
That makes sense.
So this is the art of firmware and soft computer engineers, right? To enable digital control of the system, right? And they don't just satisfy with one point, right? Then here they can create software clock, and they sample maybe 100 around this with no calculation of the main interrupt, right? Okay, so you'll do this as well. So anyway, so I think this is one technology. Now you want to do your own thing. So again, you go back. I think we may have some. Do we have any, Zahin, do we have any sample for current sensors for them?
As a PCB or as a,
No, like the sensor that they should use, no, right? So again, you go back to your sensors you discuss. So you're looking for current sensors. So you have 3,700 options. So you go to active, stocks, you don't care about the rest. Now you have 1,000 options, right? So now you start trying to reduce using this filter. Unfortunately, I mean, I think even you don't have to think about it. What I'm saying is you wanna maybe change some methods, because sometimes, you know, this filtering, I think you got that in Amazon as well. Basically, you may isolate some because it hasn't been identified the way that it is. But in this case, what you're looking for bidirectional sensor. So you have an AC current, you want to be able to measure both AC and DC current all together. So here, either you can choose this or not. And depending on your understanding, maybe you want to do different sensor type, right? So as you can see, you can go through this and choose and discuss, basically defend your design. Or you can come here and set actually the range. The range perhaps is the easiest. So I think you guys are designing with 300 watt system. I think that, Zahin, what's the power rating of the test that you conduct? I think it's about 100 watts, right, at 20 or 30 volts.
that's really different.
Okay, so it's 30, 100, 3 amps DC. So if you pick 80% duty cycle, 30, 24, 3, basically it's about 5 or 6 amps you need on the AC side, right? So 5, 6 is the range that you're good with. So I go with 10 amps, for instance, right? So 10 amps is the maximum. If you want to design to use it later with one of our PV panels, maybe you want to go all the way to 300 watts, right? Measure the current and go to the maximum, which is like 20, 25 amps. So in other words, you don't need 6 milliamp version, you don't need thousands of amps, right? So I select plus minus 20, all of this, to to 10. So now you have 160 option. Maybe you just need one channel. 150. Right? So now, between this, literally you can choose any of them. So now, anything else I can do? Maybe you have constraints on the price, you wanna see how much it can be. So this is
Box.
$366, right?
How many in a
So-
box, though?
So you wanna see if that's good enough, and you see that it's only for AC measurements, right? So maybe I also remove that. Whoever, so I select AC DC. Two. Okay, so this is 300. So again, each of them gives you some information about, like,
That's way too much.
okay, is it good enough? Is it bad? Should I go lower?
There we
Right?
I traded for 20 years.
So for instance, these are similar to what I found, right? So you see it's quickly dropped to,
go. That's only one
you
trade.
know, like $20, right? So,
How many are in a tray? 40?
so all of them, I think, are options. Now maybe you want to select, so you have Ecgr systems, for instance. I like AKM. We have Texas Instrument. We have basically our company here, Telai, but it's expensive, so we don't consider that. So Melexis is good, right? So you have 42 choices. So now I think this is the discussions that you guys wanna have, right? About the soldering of this, right? Some of them may have the, basically, underneath pad that requires oven to solder it. We have the oven, but I don't know if you have time to now learn how to use the oven, right? So you wanna exclude that. But let's say you wanna go with the first one, right? Let's go now, the cheapest one. So you see this one, for instance, pretty good. So Ecgr, so it's $1.5, right? 15 amps, 19 volts, and DC to 100 kilohertz. You're doing switching at 30 kilohertz, so this should be sufficient, right? So again,
Accuracy.
here
It's
you're
5%.
trusting that this everything is good enough, right? So you don't know, right? So
Jeez.
now here you can
That's
do a
right.
little bit of more justification, making it more aggressive in terms of frequency or confine it. So let's just, without any, it's just my personal preference, but I don't necessarily recommend. Is basically imagine that you go with this model,
Okay.
right, AKM. So as you can see, if you buy one, it's $6. If you buy 10, it's $5 each. So you see, it has 3-volt output, right? So it's bidirectional. Again, I have to double check again. But regardless, it gives you 3 volts. So you have an option to directly interface with the microcontroller now. So they did all the conversion. So one thing that then you have to see is now, see, okay, we read this, so how much voltage I should apply or support? So 5 volts, right? So in your design, you decide whether you want to use the benchtop power supply, like 5 volts, or you want actually a regulator on board. I always recommend to put a regulator on board, right? But your system may work without it. Okay? So 5 volts. Look at this. So the current can go between 20 and minus, negative 20. Look at the zero current. So if there is zero current, you see, the output is set at 1.5. So in other words, if you have 20 amps, the output is 20 amps, is 3 volts. If the output is 0, what's the actual current?
Zero.
So you see the 0 current, so if in your circuit there is no current, right,
The
at
output
0,
voltage would be
sinusoidal
1.5.
at 0, it says the output of this sensor, this transducer, is 1.5 volts, right? If it's 20 amps,
Zero.
right, what's the output of the sensor?
Zero.
If it's 20, positive 20,
Oh, positive
3 volts.
3.
3 volts, right? If it's negative 20,
Zero.
0,
Mm-hmm.
right? So the full range, 0 to 3. Does that make sense or no? Okay.
It said it was rated at 15 amps,
Where is that?
when on the, before when you were doing the filtering.
In the data sheet.
It says 5 amps. Sensitivity note.
But it also says, 20 plus or minus.
You can take 20 in, but
Yeah,
it's
linear sensing range is
Oh, okay, that's.
negative 20.
Yeah, so
20.
So it's rated for 20 amps.
So if it's 20 amps, it's basically
But
hit 3 volts.
for a 1 millisecond response time, you can only do 5 amps.
Right. Yeah. Okay? So in other words, technically speaking, you don't need anything, no buffer, nothing,
Oh, it's
right? So you pick this, right? One thing that you look for is, well, okay, it maintains the things, you may wanna read this. I don't think you understand or appreciate now. Typically, they give you the circuit examples, right? So here is the sensor, here's the microcontroller, right? Essentially, you don't have to understand this, copy, right?
sad.
Okay? Did I use this? No, I don't use this circuit. Right? So this is something, that's what I'm saying, right? The correct way, right, is to use this circuit. Do I do it? No. Right? Because I have a past experience and I know certain circuits, right? But this is what you can, basically seek advice and guidance, questions from the manufacturer. Hey, how do we get this one? And it looks like it's pretty simple. Some of them are essentials. So for instance, it requires reference, you have to understand that, right? But the output, you see, through just the low pass filter because of possible noises, right? It goes to the output. The rest, copy. Okay? So what I do, I use the same thing, don't get me wrong. I may be more conservative and I use a buffer circuit as well. Right? So I use a buffer circuit in between. Right? So why did we use buffer circuit? The voltage follower? Yeah.
High impedance output voltage,
What's the benefit?
it's a cleaner signal.
Cleaner signal? Yeah. So essentially you don't load your detector, right? So if you don't have this, everything that requires this interface, right, was done through the sensor, right? So the power supply of the sensor, right? By doing it, essentially, as you said, the high impedance, so nothing goes through this, so it's just the voltage. and the power supply of this op-amp provides, you know, whatever power is required, maybe low impedance in the for that.
So essentially it's a relay, in a very crude sense.
Relay. I don't know.
Oh, it's fine, sorry.
Yeah, so it's a buffer. Yeah, voltage follow. Right? So I always use it, but you see the manufacturer says you don't need it. So it's nothing, it's not a big deal, right? So that's on the schematic capture point of view, like, okay, what component? One thing that I noticed, again, next week perhaps becomes more clear, we tend to finish our design and then buy components. And you see that this happens to you as well, right? But I think once you guys chose this and start working on it, why do you wait? Order then. So even without the design, once your BOM is clear, I can bet 90% or 80% of the circuit remains unchanged, right? Order 80% have it, then you have 20% left, maybe different resistor value, different op amps, you know, different connectors. So that's that. After this, you're looking for any recommendation, right, that this may have. Some of them are in the data sheet, some of them not in the application notes, right? So, but just think about it, that unfortunately these sensors are supposed to be basically easing up the work, which it is. Otherwise you had to develop a sensor and all the circuitry. But it's, you know, basically how can I implement? And in this case, they provide the most conservative way, which as the painter of this, you may want other things there. But what you can see is there are always empty spaces, right? That you should provide clearance, not because of the voltage, but because of magnetic field manipulation. These are magnetic fields, right? And you use magnetic detector, which has higher sensitivity than other components, so they don't want anything around it, right? So they provide, so that's number one. Number two, you see, although your sensor is just sitting here, as simple as that, but you see the top and bottom layers are filled with coppers,
Yes.
right, at different points. So these are things, right, that they do to basically cool down the sensor. Because this sensor carries like 20 amps in this tiny IC, right? So therefore, there are some thermal consideration as well when you choose. So is that the only sensor? No. As I said, if you had some past experience with me, right, and I have no price constraint, I have good experience with that, right? But the correct way to start with was, if you don't have anything and all the things met your thing, you have to go with this, right? So basically $1, right? Good amount, 40,000 in stock, you have less risk of inventory, right? So now, as I said, you can read whatever it is, but what you need
That's the one with the plus or
is
minus.
the data sheet. So Hall
5%.
effect, doesn't matter, so we come here. Sometimes it says like, what's the typical application, right? That may help you. So it comes in two different packages. So now you want to see which one you want to use. So this one is a SOIC package. So the pads that you need to provide is very different than this one, right? So this one perhaps it's better to be soldered on the oven or you wanna use,
Wait, guide.
heat gun. Typical application, so they have this ACS 711, so this current going in the output. So you see that's, they have provided nothing for that, apparently you can use. So let's see. So this is maximum 7 volts. Functional block diagram. Let's go to the data sheet. Okay. So supply voltage, you can go 3 to 5 volts. It says typical 3.3 volts. And 100 kilohertz bandwidth. Outputs. So the current can be plus or minus.
It's right next to it.
Yeah.
I'm looking for the zero current voltage.
It's all come together.
Response. 1, 2, 3, 4, 5. That's sensitivity. Full range. Okay.
Zero current voltage. So here, again, like the other case, you see, if you apply 3.3 volts, right, it's basically times half. If you apply 5 volts, it becomes 2.5. Right?
Oh man.
So now tell me, if it's full range, if I feed 5 volts, full amps, let's say 20 amps or 15 amps in this case, what's the output of this sensor if it's 15 amps? Biased at 5
A
volts.
third divided by 2. 1/6, whatever that is.
5 volts, right? That's the maximum. And if it's negative 15, it's 0. Can I input 5 volts output to my microcontroller?
No.
No.
Yeah, right? You have to know, basically, reduce it to 3 volts, right?
And then you
So
gotta
it's
worry about that.
in other words, the conditioning circuits that you're building, right, consist of gains, right, and filters and buffers. But depending on what component you choose and what conditions you're applying, in this case, for instance, you're seeing that your op-amp functions best with 5 volts, right? Not 3 volts. And you don't want to use regulator. So you have only one bus of 5 volt in the system. Then you have to come up with this conversion. Whereas you say, well, I provide 3 volts to the sensor and the sensor accepts 3 volts, right? And that simplified the gains. So I designed the whole process assuming that I do not overload my microcontroller. Right? So again, I have some recommendations for the sensors, but really, I mean, it's up to you what you guys want to pick. Again, you need two circuits, one current sensor circuit for AC side measurements, and you need voltage measurements at minimum DC side, right? But in general, we measure both DC current, DC voltage, AC current, and AC voltage in practice. So your lab will be announced soon. Is it ready now, or Zahid?
Will be announced by Saturday.
Saturday? Alright, so your lab, basically we want at the minimum of these two conditions, to this circuit. We like to see the bomb, right? But this is not by any means something that you have to deliver that. You can pick anything. Your circuit could be completely wrong in function, right? But what I want to see is you have the schematic, you have the PCB layout. This layout has been uploaded to one of the manufacturers, including forpcb.com, and you receive feedback from them that this board can be manufactured, and there is no error from manufacturing. They don't check it's working for your purpose,
Of course.
right? So essentially, your deliverable would be the screenshot, right, of the approval from the manufacturer, right? So we don't review your BOM, we don't review your schematic, right, unless you want me to, right? But I want you to go through this process so you understand that, well, what's the process of ordering, right? And then you have a month, you have about a month or two to finalize it, to order. So I think from now on, again, we have very soft dues, right? If you can finish everything by next week, you're done with this class, right? So we have the power converter, we have the microcontroller. So this sensor board, right? Again, I'm telling you, it costs you perhaps, how much is it now with JLCB? You haven't ordered?
What's the name
I mean, there are a lot of things like JLCB, it's like Chinese, lots of names after it. What is
Oh,
it?
no.
JLC?
of it? Look.
What is it?
JLC.
JLC, yeah. JLC.
Look, yes.
The other one that I ordered, what is it?
We have a certain criteria we have to meet.
Oh, PCB way. PCB way.
We're not ordering.
PCB way. I remember we ordered for $7. It's a very good, like, very complex for $7. I couldn't believe it,
I'll pay 70.
right?
You're gonna still be rude this time.
So I think just order, in my view, but you don't have to, because you'll see that you cannot decide on the order button. You know that, okay, I can do better, right? And I'm sure you can, right? But when it comes back, then you see the problem. So that's what I think. It's better that you go ahead and order. You have this chance.
Alright. Build
did
it
it.
tonight, order it tonight.
Any question?
Is it not?
Is there limitations, like one layer PCB, anything like that?
I do not have, right? We don't have one layer PCB. I mean, you can't, but it's very hard to design one layer PCB.
Okay,
So you need 2 layers
okay.
at least, but 4 to 6 layers makes your life easy.
Okay, but more expensive.
No,
Okay.
that's what I'm saying. Here it's more expensive, but for them, no.
For Daniel, it's more expensive.
Yeah,
You can't order from us. I gotta pay Taiwan before I get
So
it.
my student, so one of my students ordered, I think 10 layer, 12 layer in one class.
Okay.
very complex design,
Mhm.
almost like an IC, if you think about it,
Okay.
for power. Didn't cost us anything. Yeah. All right, so next week we'll do PCB tutorial, but again, I highly recommend
Right. Might as
if
well.
you can do it yourself, watch some videos. We have the video on Canvas. Because maybe, I'm pretty sure other software are easier, but this is very professional. And that's it, I guess. I think it's gonna be too much if I wanna talk about grounding issues.
Vias or
Yeah. Huh?
like vias or something else?
No, it's on laying out, there are some considerations, but I like that you have the first tutorial, so you see the PCB and then the top. All right,
Thank you.
Yeah.